Hello, everyone. This is the video for conducting and interpreting a single sample t-test. And I am in the bots survey here. This data is combined from several semesters, but this is the data set that we've been analyzing in class with, it has about 200 participants in here. And so I am going to do the single sample t-test for the sleep example that we did for the lecture example for the single sample t-test. So the question is whether Abington students are getting the minimum recommended amount of sleep, which is 7 hours. So to do this single sample t-test, we're going to go to Analyze, and then we are going to go to Compare Means and Proportions. And then we are going to do a, SPSS calls it one sample t-test here. So single sample, one sample t-test. And then you should get this window that opens where you have all your variables on the left, and then you have a test variable box here. And so this is where we're going to bring our sleep variable over. And you can make this bigger, make sure that you're grabbing the right variable here. So here's the sleep variable number 2. Bring that over to the test variable box. And then here, test value. Again, this is the numeric benchmark. The test value is the numeric benchmark in SPSS. And so we'll set that to 7. And then we have the box here checked that says estimate effect sizes. That is, SPSS will calculate Cohen's d for us. Again, this is a newer option. SPSS finally added Cohen's d calculations to the program, which is fantastic. Right. And then I always recommend that you paste and then run the syntax. So we're going to paste. Boom. You should get a new syntax window. These windows are opening on another monitor. There we go. So here we see the syntax for the t-test here. And so we're going to highlight and then run. And then we should get an output window with our results. There we go. There is our output window. And so we see the tables that we saw in class. I'm not able to easily cross out the stuff that we don't need, but we'll see here in the statistics box, we see that we have 200 people in our sample, and then we see the mean for our sample, 6.51 hours, standard deviation of 1.28, and then we have our standard error here, 0.09. And then we have the t statistics down here, and then we have our Cohen's d table down here. And remember, for a single sample t-test, the formula or equation is m minus mu over standard error of the mean, right? M minus mu over standard error of the mean, or SM. M minus mu, right? So that would be m minus mu, so 6.51 minus 7. That would give us our mean difference, which we see in the second table here, right? So 6.51 minus 7 gives us negative 0.49. So that would be our numerator. And then our denominator is the standard error of the mean, SM, which is 0.09. And remember, the formula for SM is standard deviation over the square root of n. So SPSS took the standard deviation, 1.28, and then divided by the square root of n, so the square root of 200, and that gives us 0.09. And then to calculate the t-value, we find the t-value in the t column here, negative 5.47. SPSS took the mean difference, and then divided by the standard error. and that gives us our t value here. And then SPSS using the t value and technically df here, SPSS then finds the p value, and again we look at the two-sided p column here, and we see that the p value is less than 0.001, right? It's just really small. Like if we double click on that table and then double click on here, like it is really, really small. It would be 0.00000001359. So it's just really, really small. It's less than 0.001. But again, p value can never equal 0 because that would mean that we're 100% certain that the observed difference here, the observed mean difference, right? We would be 100% certain that the mean difference is far enough away from 0 to indicate a true difference. And we're never 100% certain. There's always going to be some level of error in our sample. Right? This mean is an estimate of what's going on in the population, and with estimates come error. Anyways, so p-value less than 0.001, right? And p-values are significant if they are less than or equal to 0.05, and 0.001 is way less than 0.05. So we do have a significant difference, right? So if we do 1 minus p times 100, that will give us the percentage confidence, right? So this would mean we're a p-value of 0.001, we would be 99.9% sure. So we're more than 99.9% confident or sure that this observed difference is far enough away from 0 to indicate a true and real difference after accounting for sampling error. But a significant difference does not mean it's an important difference. And so that's why we need to calculate effect size and take in consideration study context. And so we have the third table down here, which has Cohen's d, which Cohen's d is the effect size for mean difference. Well, it's one effect size that you can calculate for mean difference. It's probably the most used, most popular, safest decision to use. So if we look in the Cohen's d here row here, right? And so to calculate Cohen's d, SPSS takes the mean difference, m minus mu, divided by the standard deviation. So mean difference, negative 0.49, divided by the standard deviation, which you can also find here in the standardizer column, 1.28. So mean difference divided by standard deviation will give us negative 0.39. So the column that has the point estimate here, that is Cohen's d, so the negative 0.39. And according to Cohen, this is a small difference, right? It's in between 0.2 and 0.49, so it would be a small difference according to Cohen. But small differences, as we talked about in class, can be important differences given the context. So if you think about the difference here, the context, right, 6.51 versus 7 hours, right? So this is about a 30-minute difference, right? And if we wanted to calculate the exact minutes, we would actually take the negative 0.49, or 0.49, we just do 0.49 times 60, because there are 60 minutes in an hour, right? That would give us 29.4 minutes. So essentially, I'm just saying 30 minutes, right? There's a 30-minute difference between your average and the minimum recommended hours of sleep. And as we talked about in class, most people, I think, agreed that they'd much rather get 7 hours than 6.5 hours. That 30 minutes seems like an important difference there in terms of feeling physically better, feeling mentally better. That 30 minutes seems like it would matter, right? And it's an empirical question, right? We can do some experimental studies. We can probably look at the literature and see what sleep experiments have been done. Looking at differences of 6.5, 7 hours of sleep, and see if that 30 minutes really seems to make a difference. So it seems like it's going to be a meaningful difference. Probably the safest bet is to say it may be a meaningful difference, but it certainly does not seem like it's not at all important. especially given the importance of sleep in our lives, and all the how sleep affects so many things from maintaining a healthy weight to being cognitively alert. Sleep is important. So that is the single sample t-test in just about 10 and a half minutes. And yeah, there we go. Hopefully this was helpful, revisiting the single sample t-test in this video, letting you know how to do the single sample t-test and then how to interpret the output. Thanks, guys.